nitrogen-vacancy center defect in diamond has become a potential candidate for a number of applications. This ranges from magnetometry to high spatial resolution imaging to quantum computation. At low temperatures, optical transitions and the nitrogen-vacancy center become very narrow and can be coherently manipulated. This can be used to explore further interesting applications such as spin photon entanglement generation and optical control. A detailed understanding of the electronic and vibronic properties of the defect is necessary to reliably control and manipulate the spin state of the defect. The vibronic properties of the defect may be manifested in the absorption or luminescence spectra. In the absorption process, the transition starts from the 0-point vibrational ground state of the electronic ground state. The 0-point vibration ground state always transforms as A1, while the electronic ground state transforms as 3A2 in nitrogen vacancy center. The transition may end at the excited local vibration states of the electronic excited state. The electronic excited state transforms as 3E in nitrogen vacancy center. In the luminescence process, one starts again from the 0-point vibration ground state and may end at the excited local vibration states of the electronic ground state of this defect. Indeed, Davis and Hammer measured the absorption and luminescence of the defect at liquid nitrogen temperature, showing small peaks in the vibration sidebands associated with the local vibration modes of the defect. They observed a very peculiar feature of the first peaks around 60 mV near to 0 phonon line. It was a singlet in luminescence while a doublet in absorption. Davis and Hammer interpreted this effect as the tunneling of nitrogen atom from one side to the other side of the defect. We calculated this barrier energy and it is very high withstanding this motion, thus the doublet feature in absorption should be explained by an alternative model. We studied the vibration modes by first principle plane wave supercell calculations. We allowed to vibrate all of the atoms in the supercell, thus we applied a relatively small supercell in order to make our calculation feasible in our computer clusters. Correspondingly, we applied a 4x4x4 Monkr's K-point set in order to sample the brilliance zone. The calculated local vibration modes are shown in the table. According to the group theory, two fully symmetric A1 modes and two degenerate E modes should appear under C-series symmetry if a 4-atom model of the nitrogen vacancy center is applied. Indeed, we found two A1 modes and two E modes localized on the defect. The calculated local vibration modes are very similar both in the ground and excited states, thus we show these modes only for the electronic ground state. As you can see here, the EX motion of the nitrogen atom shown in blue and the nearby carbon atoms as in yellow colors. An AY motion also breaks the symmetry of the system. However, the A1 mode here conserves the C-series symmetry of the system. In this case, the nitrogen atoms moves a lot, and this is also true for the next E modes where nitrogen moves a lot, breaking the symmetry both for EX and AY motions. However, for the next A1 mode, nitrogen does not move a lot. Now, for the discussion, it is important to analyze the electronic states too. The electronic ground state transforms as 3A2, which is non-degenerate, and the unpaired electrons are localized on the carbon side, while the electronic excited state is an E mode, which is double degenerate, and the unpaired electron partially localized on nitrogen too. As a consequence, we assume that only those vibration modes are coupled to the transition in the absorption, where the local modes are localized on the nitrogen atom. And because this electronic excited state is double degenerate, therefore the E and A1 modes can both coupled. However, in the luminescence, because the end state is a singlet state, therefore only the A1 mode can be coupled to the transition.
So the final picture is the following: that the singlet mode in the luminescence can be explained by the by the non-degenerate electronic ground state, while the doublet in the absorption spectrum may be explained by the strong coupling of the A1 and E modes to the electronic excited state.